Hello, my name is John K. Mathai, and I'm a PhD student at the University of Illinois under Dr. Hans Stein. Today I'm privileged to share with you some data on the effects of heat treatments on soybean meal and how those can affect the nutrient availability therein. Now, everyone listening is probably familiar with the idea that corn and soybean meal blends are really the backbone of modern North American swine diets. And so, as a nutritionist, we're concerned with the variability that is intrinsic to these ingredients because we formulate precisely, and in terms of production, precision is money. So it's important for us to really understand the sources of variability in the ingredients that we're using, and ideally we want to eliminate the sources of variability if possible. Now in reality, that's not always within our ability, and so our job is then to understand the sources of variability so that we can really increase the efficiency of the utilization of these ingredients in our diets. Now specifically today we're going to be talking about soybean meal, and we're talking about heat damage. And we know that heat damage is a major source of variability in soybean meal. And predominantly, when people talk about heat damage in soybean meal, often what's brought up is the effect on amino acid digestibility, particularly in terms of reduced digestibility or bioavailability, if you want to call it that. The problem with heat is that it's a quote-unquote necessary evil, at least in terms of soybean meal processing. And that's because we use the heat to desolventize our soybean meal. We use solvents like hexane to extract the oil. So we heat it afterwards to promote hexane's evaporation. And even if you're using crushing, there's the intrinsic heat brought by the friction of that process. And at the same time, in order to make soybean meal an effective proteinaceous ingredient in our diets, we need to heat it to inactivate those anti-nutrient factors like trypsin inhibitors. So heat, in a way, is a double-edged sword. And when we're talking about heat, we're really talking about the Maillard-Hodge reaction. And what that is basically we have a reducing sugar, an aldose, with its carbonyl group on its end, and it undergoes a condensation reaction in the presence of heat and moisture. That aldose condenses with an amino group on an amino acid, resulting in a glycosylamine, meaning you have a combined sugar and amino acid compound. And the problem with these compounds is that they cannot be used by the animal for protein deposition or protein synthesis. So as I mentioned earlier, often when we're talking about the Maillard reaction, people are looking at it in terms of amino acid digestibility. But something that we began to wonder about was the energy question. How does heat damage affect the energy availability of these nutrients? And at the same time, how is the Maillard reaction a factor of time and/or temperature? And so with these questions in mind, we decided to examine the effects of heat treatment on soybean meal through a series of experiments. And in this case, we went through two experiments where we determined the amino acid digestibility and the digestible energy and metabolizable energy concentration in heat-treated soybean meals. And so for these two experiments, we used the same batches of ingredients, and I'll explain the ingredients that we use here. We start with our conventional high-quality soybean meal, and then if we didn't treat that soybean meal, meaning that we didn't add any further heat treatment, we left that as our control. Then we took some of that soybean meal and we autoclaved it. And we autoclaved it at two temperatures, 110 degrees Celsius and 150 degrees Celsius. And so we have two groups within temperature. Now within temperature, we heated for different amounts of time. So at our low temperature, 110 degrees Celsius, we heated it for 15 minutes or for 30 minutes. And then at our high temperature, 150 degrees Celsius, we heated it for between 3 to 18 minutes. And so what that means is that, in essence, we have 8 heat-treated soybean meals and 1 control. And so we used those ingredients for both experiments. Now before we jump into the results here, just to double check that we really achieved the Maillard reaction, if you look at the analyzed lysine content in one of the diets we used in this experiment, we see that, if I set up the slide here very quickly, on the left-hand side we have our control, our completely conventional soybean meal in blue. Then we have our low temperature here in green, which is our 110 degree treatment, and underneath that, the 2 time periods on the x-axis. And then to the right, our high temperature treatments in the red, and then the time periods below on the x-axis. You can see that as the temperature increased, now there's no statistics here, but we can clearly see that as the temperature increased, we saw a reduction in the analyzed lysine concentration. And we can see that as the time increased, we saw a trend for it to decrease as well. And I should note that if you look at the analyzed concentration of the amino acids in this diet, you see this both in arginine and lysine quite markedly. And that makes sense because both of these amino acids have terminal amino groups. So if we look at our first experiment, and that's to determine our amino acid digestibility in our heat-treated soybean meals, we'll go to the materials and methods first. And to explain the diets quite briefly, we have 10 diets, and 9 of those diets are formulated with each of our soybean meal treatments that we created. And in those diets, all of the amino acids came from the soybean meals. We also used one nitrogen-free diet, and that was so that we could determine endogenous losses and calculate our standardized ileal digestibility values. It's worth noting that these pigs had ad libitum access to feed and water. So in this experiment, we had 10 ileal cannulated barrows, with an initial body weight of around 37 kilos, and we had a 10 by 7 Udin square, so that's 10 treatments and 7 periods. And each of those periods were 7 days long, and within those periods we had a 5-day adaptation, and for 2 days we collected ileal effluents. So if we jump right into the results here, when we look at the standardized digestibility of lysine, and you can see the slides are set up similar to what you've seen before, the control on the left-hand side, low temperature in the green in the middle, and high temperature in the right in red. I will say I'm only going to present digestibility of lysine, methionine, threonine, and tryptophan, and that's in the interest of brevity, and you'll see why as the results mirror each other. So if we look at the digestibility of lysine here, and we compare our control treatments versus our low temperature treatments, we see that there's no significant difference in the digestibility of lysine at this level of temperature and at these time periods. And then if we compare our low temperature to our high temperatures, we see that there's a decreased digestibility of lysine in our high temperature treatments. And then if we look within our high temperature treatments, as time increases, we see a linear reduction in the digestibility of lysine. And so it becomes quite easy to see a trend here. And if we take a look here at methionine, we see a very similar pattern here again. We see that when we compare our control to our low temperature treatments, there's no significant difference. However, when we compare our high temperature treatments to our low temperature treatments, again, there's lower digestibility of methionine in our high temperature treatments. And then we see, once again, a linear reduction in the digestibility as the length of time increases. So if we continue on here and look at the digestibility of threonine, and we compare our control treatments to our low temperature treatments, we see that there is no difference in digestibility. And then when we compare our low temperature treatments to our high temperature treatments, we see the reduced digestibility of threonine in our high temperature treatments. And again, as we look at our high temperature treatments, the digestibility of threonine decreases as the length of time increased. And similarly to threonine, we see the same results with tryptophan. No differences between our control treatments and low temperature treatments. We see a reduced digestibility for tryptophan when we compare our high treatments to our low treatments. And then as the length of time of heating increases in our high temperature treatments, we see reduced digestibility of tryptophan. And although I'm not presenting the rest of the indispensable amino acids, I will say that this trend was the same for all of them. So if we go to the conclusions and see what we learned from this data, we see that there were no differences in the digestibility values of amino acids at our low temperature treatment, that's 110 degrees Celsius. But if we compare the digestibility values between our high temperature treatments and our low temperature treatments, we see a reduced digestibility of amino acids in the high temperature treatments. And finally, if we look within our high temperature treatments, we saw linear reductions in the digestibility of amino acids as time increased. And so now we'll move on to our second experiment where we look at the effect of heat treatment on the concentration of digestible energy and metabolizable energy in heat-treated soybean meals. For our second study, we used 20 growing barrows with initial body weights of around 44 kilos. These animals were housed in metabolism crates where we had a 7-day adaptation to the diet and 5 days of collection using the marker-to-marker method. Now, if we move on to our diets, for this experiment we had our 10 diets, and we had 1 corn-based basal diet and 9 soybean meal-based diets. This experiment was set up as a replicated 10 by 4 Udin square, with 2 pigs per treatment, for 8 total replicates. And the pigs were fed at 3 times their maintenance requirement. And if we look at the diets a little bit more closely, our basal diets were formulated with 97% corn and 3% vitamins and minerals. And our soybean meal diets were formulated with 71.25% corn and 26% of one of the soybean meal treatments, and the remainder was vitamins and minerals. So if we jump into our results and we look at the digestible energy here of our soybean meal, we see our slides are set up the exact same way as they were with the amino acid digestibility. We have our control treatment on the left, and when we compare our control treatment to our low temperature treatment, there was no difference in the DE. When we compare our control treatment and the low temperature treatments, we saw no difference in the concentration of digestible energy. And if we compare our low temperature treatments to our high temperature treatments, we saw a reduction in the concentration of digestible energy in our high temperature treatments. And again, like we saw with our amino acid digestibility data, that as time increased within the high temperature treatments, the concentration of digestible energy decreased. Now, if we move along to our metabolizable energy, we see exactly the same trends. No differences between our control treatments and our low temperature treatments. And then if we compare our low temperature treatments to our high temperature treatments, we saw a reduction in the concentration of metabolizable energy in our high temperature treatments. And then within high temperature treatments, as the length of time increased, we saw reductions in the concentration of metabolizable energy. So if we move on to the conclusions from this experiment, we see that there are no differences in the DE or ME concentration in the soybean meal autoclaved at 110 degrees Celsius. However, we saw reductions in the concentrations of DE and ME in our high temperature treated soybean meal compared with our low temperature treated soybean meal. And then when we looked within our high temperature treatments, we saw linear reductions in our digestible energy and metabolizable energy. So if we put the conclusions from both of our experiments together, we saw that low temperature treatment has no effect on digestible energy, metabolizable energy, or the digestibility of amino acids. We also saw that at high temperature treatments, we saw reductions in the DE, ME, and digestibility of amino acids. And finally, at our high temperature treatment, we saw reductions in the DE, ME, and digestibility of amino acids as time increased. So if we interpret these results with respect to our objectives, we see that the Maillard reaction is certainly a factor of temperature, as we saw differences between our low temperature treatments and our high temperature treatments. But also we saw it's a factor of time with the reduction in digestibilities as our time increased. And so when considering time and temperature, it forms a very simple equation. The Maillard reaction and heat damage is really the effect of both time and temperature, and so both of these need to be considered when we're trying to quantify its effects. And with that, I would like to thank the sponsor of the study, Evonik, for their financial support. And I would like to thank you for your attention. I would encourage you to visit our website if you're interested more in this research, as we've done several experiments looking at the effects of heat treatment on various ingredients. So please visit our website at nutrition.ansci.illinois.edu. Thank you.